I've been thinking a lot about space and time, and it's one of those things that seems so obvious, so fundamentally different from each other, that when someone tells you they're actually the same thing, it sounds like nonsense, like complete nonsense. Because space is, well, it's the stuff around you, right? It's the distance between here and there, the emptiness between objects, the three dimensions you can move through when you walk across a room or drive to the store or fly to another country. And time is something else entirely. Time is what clocks measure. Time is the thing that flows, that moves forward relentlessly, that carries you from past to present to future. Space is where things happen. Time is when things happen. They're completely different categories of existence, different dimensions of reality, and mixing them up would be like confusing up with Tuesday or red with 7. It just doesn't make sense. Except it turns out that intuition is wrong. Completely, fundamentally wrong. Space and time aren't separate things at all. They're not two different entities that happen to coexist in our universe. They're aspects of the same thing, woven together so intimately, so inextricably, that separating them is not just difficult, but actually meaningless. The universe doesn't have space and time. It has space-time. One thing, one fabric, one unified structure. And this isn't some philosophical word game or poetic metaphor. It's the literal truth about how reality works, confirmed by countless experiments, proven beyond any reasonable doubt, and absolutely central to everything we understand about physics. But here's the thing that makes this so difficult to grasp. Our everyday experience tells us otherwise. Every single moment of your life reinforces the idea that space and time are separate. When you look around a room, you see space. When you check your watch, you experience time. You can move through space in any direction, forward or backward, left or right, up or down. But time only goes one way. You can't go back in time, can't move through it the way you move through space. Space seems static, fixed, a stage on which events unfold. Time seems dynamic, flowing, carrying everything along with it. And this everyday experience is so powerful, so deeply ingrained in how we think about the world, that accepting the truth requires us to fundamentally rewire our intuitions about reality itself. So where did this revolutionary idea come from? How did we discover that space and time are the same thing? Well, the story begins, as so many stories in modern physics do, with Albert Einstein. And it starts with a problem, a deep mystery that was bothering physicists at the turn of the 20th century. You see, there was this strange thing about light, about electromagnetic waves, that didn't make sense within the framework of physics as it existed then. The problem was speed, the speed of light. And once Einstein figured out what that problem meant, once he followed the implications to their logical conclusion, everything changed. Let me back up a bit and explain what the problem was. In the late 19th century, physicists understood that light was an electromagnetic wave, and they'd measured its speed, about 300,000 kilometers per second, or roughly 186,000 miles per second if you prefer. Fast. Incredibly fast. But here's where things got weird. When you measure the speed of something, that speed is always relative to something else, right? If you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the ground watching the train go by would see the ball moving at 70 miles per hour. The speeds add up. That's obvious, intuitive, how motion works in everyday life. But light didn't behave that way. When physicists measured the speed of light, they got the same answer no matter how they were moving. It didn't matter if they were moving toward the light source or away from it. It didn't matter if the light source was moving or stationary. The speed of light was always the same. 300,000 kilometers per second. Exactly. No variation. And that was deeply, profoundly weird. It was like throwing that ball on the train and having someone on the ground measure it moving at 20 miles per hour too, even though the train is clearly moving. It violated every intuition about how motion should work. Now, there were various attempts to explain this. Some physicists thought there might be a medium that light waves traveled through, something called the luminiferous ether. And maybe the Earth was moving through this ether in just the right way to make the measurements come out weird. But every experiment designed to detect this ether came up empty. The most famous was the Michelson-Morley experiment in 1887, which was supposed to detect the Earth's motion through the ether, by measuring tiny differences in the speed of light in different directions. It found nothing. The speed of light was the same in every direction, regardless of the Earth's motion, which meant either the ether idea was wrong or something even stranger was going on. Einstein's genius was to take this weird experimental result seriously. Instead of trying to explain it away or fit it into the existing framework, he asked what would happen if you just accepted it as a fundamental fact about the universe. What if the speed of light really was constant, the same for all observers no matter how they were moving? What would that mean? And when he worked through the mathematics, when he followed the logic to its conclusion, he discovered something astonishing. If the speed of light is constant for all observers, then space and time can't be absolute, separate things. They have to be flexible, relative, interconnected. They have to be part of the same thing. Here's how this works, and I know it's going to sound strange, but stay with me. Imagine you're standing still, and I'm on a spaceship flying past you at, let's say, half the speed of light, pretty fast, right? Now, I shine a flashlight forward from the spaceship. From my perspective on the spaceship, the light is moving away from me at the speed of light, 300,000 kilometers per second. That makes sense. But what about from your perspective, standing still while I fly past? According to classical physics, you should see the light moving at 1.5 times the speed of light, because you'd add my speed to the light's speed, but you don't. You measure the light moving at exactly the speed of light, same as I measure. How is that possible? The only way this can work, the only way both of us can measure the light moving at the same speed, is if we're not measuring the same space and time. If time is passing differently for me than it is for you, if the distances we're measuring are different, and this isn't an illusion or a trick of perception, this is real. Time literally passes more slowly for me on the moving spaceship than it does for you standing still. Not by much at half the speed of light, but measurably. And the faster I go, the more dramatic the effect becomes. If I were moving at 99% of the speed of light, time for me would pass about 7 times slower than it does for you. If I traveled for what felt like 1 year to me, you'd experience about 7 years passing. We'd both be right. Time itself is different for each of us. This is called time dilation, and it's been tested countless times. It's not a theory in the sense of a guess or speculation. It's observed, measured reality. We put atomic clocks on airplanes flying around the world, and when they land, they're behind the clocks that stayed on the ground. By tiny amounts, nanoseconds, because airplanes are slow compared to the speed of light, but by exactly the amount Einstein's equations predict. We send particles accelerated to near light speed around particle accelerators, and their decay rates slow down. Their internal clocks run slower, just as predicted. Astronauts on the International Space Station age slightly more slowly than people on Earth. Not by enough to notice in a human lifetime, but measurably. It's real. But time dilation is just one piece of this. There's also length contraction. From your perspective, watching me fly past in that spaceship, the spaceship itself would be shorter in the direction of motion than it is from my perspective. Not a lot shorter at half the speed of light, but at 99% of the speed of light, it would be compressed to about 1/7 its original length. And again, this isn't an optical illusion. From your frame of reference, the spaceship really is shorter. From my frame of reference, on the spaceship, I'm the right length, but the universe outside is contracted. Both perspectives are equally valid. There's no absolute truth about lengths, just as there's no absolute truth about time. And here's where it all comes together, where we start to see why space and time are the same thing. These effects, time dilation and length contraction, they're not separate phenomena. They're two aspects of the same underlying reality. When I'm moving relative to you, what's really happening is that our measurements of space-time, this unified four-dimensional thing that we're both embedded in, are rotated relative to each other. It's almost like, well, imagine you and I are looking at a straight line drawn on a piece of paper, but we're standing at different angles to the paper. From your angle, the line looks longer in the left-right direction and shorter in the forward-back direction. From my angle, the line looks longer forward-back and shorter left-right. We're both looking at the same line, but because we're viewing it from different angles, we break it down into horizontal and vertical components differently. That's similar to what's happening with space-time. We're both embedded in the same space-time, but because we're moving relative to each other, we're dividing it into space and time differently. What I call space, you partly call time. What you call time, I partly call space. This insight was made explicit by Hermann Minkowski, one of Einstein's former teachers, who formulated the mathematical framework for special relativity. In 1908, just 3 years after Einstein published his special theory of relativity, Minkowski gave a famous lecture where he said, and I'm paraphrasing here because the original was in German and various translations exist, but the essence was, from now on, space by itself and time by itself are doomed to fade into mere shadows, and only a union of the two will preserve an independent reality. Space by itself doesn't exist, time by itself doesn't exist, only space-time exists. And in space-time, what we call space and what we call time are just different directions, different dimensions of the same unified thing. Now you might be thinking, okay, but they still feel different, right? I can move through space, but I can't move through time in the same way. Doesn't that make them fundamentally different? And that's a fair question. There is a difference, an important one, but it's not the difference you think. It's not that space and time are different types of things. It's that there's a mathematical sign difference in how they contribute to distances in space-time. Let me try to explain what that means without getting too deep into the mathematics, which can get pretty technical, but the basic idea is actually not that complicated. In ordinary three-dimensional space, if you want to calculate the distance between 2 points, you use the Pythagorean theorem, right? You square the difference in the x direction, square the difference in the y direction, square the difference in the z direction, add them all up, and take the square root. That gives you the distance. In space-time, you do something similar, but with a crucial difference. You square the time difference, multiply it by the speed of light squared to give it the right units, but then you subtract the space differences instead of adding them. That minus sign, that's the key difference between space and time. It's a difference in mathematical signature, not a difference in fundamental nature. They're still both dimensions of the same thing, space-time, but they enter the equations differently. And this minus sign has profound consequences. It's what determines causality, what determines which events can influence which other events, what determines the structure of past, present, and future. Because of that minus sign, there's a limit to how fast information can travel through space-time. That limit is the speed of light. Nothing can go faster, not because there's some cosmic speed limit enforced by traffic cops, but because going faster than light would require moving in a direction through space-time that doesn't exist. It would be like trying to walk north of the North Pole. The geometry doesn't allow it. The speed of light isn't really about light at all. It's about the structure of space-time itself. Light just happens to travel at that speed because photons, the particles of light, have no mass, and massless particles always travel at the maximum possible speed through space-time. This is worth pausing on because it's so important. The speed of light, this fundamental constant that shows up everywhere in physics, isn't fundamentally about light. It's about the conversion factor between space and time. It's about how much space corresponds to how much time in the unified fabric of space-time. We measure distances in meters and time in seconds, but that's arbitrary, a human convention. We could just as easily measure everything in terms of time, saying that a light second is the distance light travels in 1 second, about 300,000 kilometers. Or we could measure everything in terms of distance. The speed of light in natural units that physicists often use is just 1 meter per meter, 1 second per second. It's the universal conversion factor, the exchange rate between the space dimension and the time dimension of space-time. And here's something that really drives this home. When you're sitting still, when you think you're not moving, you're actually moving through space-time at the speed of light. You're always moving through space-time at the speed of light. Every object, every particle, everything in the universe is always moving through space-time at exactly that speed. It's just that when you're sitting still in space, all of that motion is through time. You're moving through time at the maximum rate. But when you start moving through space, some of that motion gets redirected from the time direction into space directions. The faster you move through space, the slower you move through time, because the total speed through space-time stays constant. That's why time slows down when you're moving. You're using up some of your motion through time to move through space instead. I know that sounds bizarre. How can you be moving through time? What does that even mean? But think about it this way. Every second, you age by 1 second. That's motion through time. You're progressing through the time dimension at a rate of 1 second per second. And when you're sitting still in space, that's the fastest you can age, the fastest you can move through time. But start moving through space, and you age more slowly. You move through time more slowly. Not because time has stopped or slowed down in some absolute sense, but because you've redirected some of your motion through space-time from the time dimension into space dimensions. The total motion stays the same. The speed through space-time stays at light speed. But how that motion is divided between space and time changes. This is why nothing with mass can reach the speed of light. Because if you were moving through space at the speed of light, you'd be using all of your motion through space-time for space and none for time. You'd have no motion left for time. Time would stop for you completely. You wouldn't age at all, wouldn't experience any passage of time. From your perspective, the journey would be instantaneous, regardless of distance, and that's what happens for photons. From a photon's perspective, if we could imagine having a photon's perspective, it's created and absorbed in the same instant, regardless of how far it travels through space from our perspective. It doesn't experience time at all. All of its motion through space-time is through space, none through time. But let's go deeper into this, because special relativity, everything I've talked about so far, that's just the beginning. That's the theory Einstein developed in 1905, the theory of how space and time work when gravity isn't involved or when gravity is weak enough to ignore. And already it showed us that space and time are unified, that they're the same thing. But then, 10 years later, in 1915, Einstein published General Relativity, his theory of gravity. And general relativity takes the unity of space and time even further. It shows that space-time isn't just a passive stage where events unfold. It's dynamic, flexible, curved, and that curvature, that geometry of space-time, is what we experience as gravity. Here's the revolutionary insight of general relativity. Gravity isn't a force in the traditional sense. It's not something pulling on objects, not an invisible rope or attraction between masses. Gravity is the curvature of space-time itself. Massive objects, things with mass and energy, they bend space-time around them. They create curves, warps, distortions in the fabric of space-time. And other objects moving through this curved space-time follow the straightest possible paths they can, which in curved space aren't straight lines anymore, they're geodesics. Curves that are straight in the sense that they're the shortest distance between 2 points, the path you'd naturally follow if you're just coasting along without any forces acting on you. What we interpret as gravity, as falling, as being pulled toward the Earth or the Sun, is actually just objects following straight paths through curved space-time. The classic analogy, and it's used so often because it really does help, is to imagine space-time as a rubber sheet. Put a heavy ball on the sheet and it creates a depression, a curve in the rubber. Now roll a smaller ball across the sheet near the heavy ball. The smaller ball will curve toward the heavy ball, not because there's a force pulling it, but because it's following the straightest path it can through the curved surface of the sheet. That's gravity. That's what's happening in our universe. The sun curves space-time around it, and the Earth follows a curved path through that curved space-time, which we observe as the Earth orbiting the sun. You're sitting in your chair right now, and the Earth curves space-time beneath you, and the straightest path through that curved space-time would be to fall toward the center of the Earth. The chair is pushing you up, preventing you from following that straight path, and you feel that as weight, as the force of gravity. But here's what's crucial for understanding why space and time are the same thing. The curvature isn't just in space, it's in space-time. Time is curved too. In fact, the curvature of time, the warping of time by mass and energy, is often more significant than the curvature of space, at least for weak gravitational fields like the Earth's. When you're standing on Earth's surface, time is passing more slowly for you than it is for someone in orbit, someone farther from Earth's mass. Not by much, but measurably. GPS satellites have to account for this. Time passes faster for the satellites than it does for receivers on the ground, because the satellites are farther from Earth's gravitational field, where space-time is less curved. Without correcting for this time difference, GPS would be off by kilometers. And this isn't just a side effect or secondary consequence. The curvature of time is what we experience as gravity in everyday life. When you drop a ball, it falls because it's moving into the future, moving through time. And the curvature of time makes that motion through time appear as motion through space, downward. You're not moving through space at all, or barely, when you drop the ball. You're just releasing it so it can follow its natural path through curved space-time. And that path, because of how time is curved near Earth's mass, includes acceleration downward through space. It's time that's curved, and that curved time creates what we call gravitational acceleration. This is so different from our intuitive understanding of gravity, so different from the Newtonian picture of forces and attractions, that it's worth emphasizing just how well tested this theory is. General relativity has been confirmed by countless experiments and observations. The bending of starlight around the sun during a solar eclipse, first observed in 1919, showed that light follows curved paths through curved spacetime. The precession of Mercury's orbit, a tiny shift that Newton's theory couldn't explain, was perfectly predicted by general relativity. Gravitational time dilation has been measured with atomic clocks at different altitudes. We've detected gravitational waves, ripples in space-time itself, created by colliding black holes and neutron stars, exactly as Einstein's theory predicted. General relativity isn't speculation. It's how the universe works, tested and confirmed over and over again. But let's think about what this means for our understanding of space and time as the same thing. In general relativity, space-time is a physical thing. It has structure, geometry, properties. It can be curved, can be stretched, can even ripple and wave. It's not empty nothingness. It's not just a coordinate system we use to label where and when things are. It's a real physical entity, as real as matter or energy. More real, actually, because matter and energy are things that exist in space-time, and their existence changes the shape and structure of space-time itself. There's a deep interplay, a feedback loop. Matter tells space-time how to curve, and curved space-time tells matter how to move. That's the essence of general relativity, captured in Einstein's field equations, which are beautiful and profound and complex enough that solving them requires serious mathematical effort. And in this picture, space and time aren't just unified in the sense that they're mixed together or that measurements of one depend on measurements of the other. They're unified in the sense that they're literally the same substance, the same fabric. Space-time is one four-dimensional manifold, one continuous structure, and the dimensions we call space and the dimension we call time are just different directions within that structure. They're no more fundamentally different than north is from east. North and east are different directions, sure, and they have different properties, but they're both directions in the same two-dimensional surface. Similarly, space and time are different directions in the same four-dimensional space-time, and they have different properties, that mathematical signature difference I mentioned, but they're both directions in the same thing. Now, there's a question that often comes up here, and it's a good one. If space and time are the same thing, why does time feel so different? Why does it seem to have a direction, a flow, when space doesn't? Why can we remember the past but not the future? Move toward tomorrow but not toward yesterday? This is the arrow of time problem, and it's one of the deepest mysteries in physics, because general relativity and special relativity and quantum mechanics, all the fundamental laws of physics that we know, they don't distinguish between past and future. They're time symmetric. They work just as well running forward or backward. The equations don't care which direction is future and which is past. If you could watch a movie of elementary particles interacting and the movie was played backward, you wouldn't be able to tell. The interactions would still obey all the laws of physics. So where does the arrow of time come from? Why does the universe have a direction to time? And the answer, we think, has to do with entropy, with the second law of thermodynamics, with the statistical tendency of systems to evolve toward more disordered states. The past is the direction of lower entropy, the future is the direction of higher entropy, and we remember the past because memories are low entropy records, organized information, and those naturally form in the direction of increasing entropy, not decreasing. But that's a whole other topic, really, and I don't want to get too sidetracked. The point is that the apparent directionality of time, the flow of time, isn't fundamental to space-time itself. It's an emergent property, something that arises from particular conditions in our universe, from the fact that the universe started in a very low entropy state at the Big Bang and has been evolving toward higher entropy ever since. At the fundamental level, at the level of space-time itself, time is just another dimension, no more inherently directional than space is. And that brings us to another profound implication of space-time being a single, unified thing. If space and time are the same, and if the laws of physics are time-symmetric, then in some sense, all of time exists at once. This is called the block universe view, and it's a natural consequence of relativity. In the block universe picture, space-time is a four-dimensional structure, and all events, everything that has ever happened or will ever happen, exist as points in this structure. The Big Bang exists. The formation of Earth exists. You reading this right now exists. Your death exists. Everything is laid out in space-time, a vast four-dimensional landscape of events. Now, this raises disturbing questions about free will, about the nature of consciousness, about whether the future is predetermined. If all moments in time exist equally, if your future self exists in space-time just as much as your present self, then is the future fixed? Is everything that will happen already determined, or is there still room for choice, for freedom, for genuine novelty? These are deep philosophical questions, and honestly, we don't have definitive answers. Some physicists and philosophers accept the block universe and argue that free will is an illusion, that our sense of choosing is just an experience, a subjective feeling that doesn't correspond to any real openness in the future. Others argue that quantum mechanics introduces genuine randomness into the universe, that the future isn't determined even if it exists, or that consciousness and choice are real phenomena that don't fit neatly into our current understanding of physics. I tend to think, and this is just my personal take, not something I can prove, that the block universe is probably the right way to understand space-time, but that doesn't necessarily mean free will is an illusion. It might mean we need to reconceptualize what free will is, what choice means in a universe where all times exist equally. Maybe free will isn't about the future being open and undetermined. Maybe it's about the fact that our choices, our decisions, are part of what determines the structure of space-time, part of what makes the universe the way it is. Maybe saying that your future self exists in space-time is just saying that you will make certain choices, not that you're forced to make them by something external to you. The philosophical issues here are subtle and complex, and I don't want to pretend there are easy answers. But let's come back to the physics, to the structure of space-time itself. One of the most important concepts for understanding space-time is the light cone. Imagine you're at a particular point in space-time, a particular place and time. Call it an event. From that event, you can draw the paths that light rays would take if they were emitted from that point, moving forward and backward in time. These paths form a cone shape, the light cone. The future light cone consists of all events that could be reached from your event by traveling at or below the speed of light. The past light cone consists of all events that could have sent signals to your event by traveling at or below the speed of light. And here's the key insight. Your future light cone defines the events you can causally influence. Your past light cone defines the events that can causally influence you. Events outside your light cone, events that are space-like, separated from you, those events can't affect you and you can't affect them. They're outside your causal reach. For those events, the question of whether they've happened yet or not hasn't happened yet is ambiguous, depends on your frame of reference. Different observers in relative motion would disagree about the order of events outside each other's light cones. But events within the light cones, events that are time-like separated, those have an absolute order. Causes come before effects. The past light cone is the past, the future light cone is the future, and events outside the light cone are elsewhere, in a region of space-time that's neither past nor future relative to you. This structure, the light cone structure, is fundamental to space-time. It's what defines causality, what defines the possible relationships between events, and it's the same for everyone, regardless of their motion. Different observers might disagree about how much space and how much time separate two events, but they'll agree about the light cone structure, about whether one event can causally influence another. That's invariant, unchanging, the same in all reference frames. And that invariance, that shared structure, is what makes space-time a coherent, unified thing rather than a jumble of contradictory perspectives. There's also the concept of proper time, which is worth understanding. Proper time is the time measured by a clock moving along a particular path through space-time. It's the time experienced by an observer following that path. And proper time is an invariant quantity, the same for all observers. If you travel from event A to event B along some path, your clock will record a certain amount of proper time, and everyone, regardless of their motion, will agree that's how much proper time elapsed for you. Or they might disagree about how much coordinate time elapsed, how much time passed in their reference frame, but they'll agree about how much time you experienced, how much your clock advanced. And here's something fascinating about proper time. Different paths through space-time between the same two events can have different proper times. If you take a straight path through space-time from A to B, just coasting along without accelerating, that path will maximize proper time. It'll be the longest time you can experience between those events. If you take a curved path, accelerating and changing velocity, you'll experience less proper time. This is the twin paradox. One twin stays on Earth, the other travels to a distant star and back at high speed. When they reunite, the traveling twin will have aged less, experienced less proper time, because they took a curved path through space-time, while the stay-at-home twin took a straight path. This seems paradoxical because from symmetry, you might think each twin could consider themselves stationary and the other moving, so each should age less than the other, which is impossible. But the asymmetry comes from acceleration. The traveling twin has to accelerate, has to turn around, has to follow a curved path through space-time. The stay-at-home twin follows a straight path. And in space-time, straight paths maximize proper time, maximize aging. It's the opposite of ordinary space, where straight paths minimize distance. In space-time, because of that minus sign I mentioned, straight paths maximize time. Curved paths give you less time, not more. All of this, all these features of space-time, they come from the fundamental unity of space and time, from the fact that they're not separate things, but aspects of a single four-dimensional structure. And this unity has practical consequences, real-world effects that we observe and use. GPS relies on both special and general relativistic corrections. Particle accelerators have to account for time dilation. Gravitational lensing, the bending of light by massive objects, is used in astronomy to observe distant galaxies. The existence of black holes, regions where space-time is so curved that not even light can escape, is predicted by general relativity and confirmed by observation. We've even detected gravitational waves, ripples in space-time itself, traveling at the speed of light, just as Einstein predicted over 100 years ago. The detection of gravitational waves is worth dwelling on for a moment because it's such a direct confirmation that space-time is real, physical, something that can wave and ripple like water. In September 2015, the LIGO observatories detected a gravitational wave from two black holes colliding over 1 billion light-years away. The wave, as it passed through Earth, stretched and compressed space-time itself by an incredibly tiny amount, less than the width of a proton. But LIGO is sensitive enough to measure that, and what's being measured isn't some force or field propagating through space. It's space itself and time itself, oscillating, stretching, and squeezing. Space-time is the thing that's waving, not something in space-time, space-time itself. And these waves travel at the speed of light, as they must, because gravitational waves are disturbances in the fabric that defines what light speed is. They can't travel faster than light because nothing can travel faster than light, not because of some cosmic speed limit, but because the speed of light is the speed of causality, the speed of space-time itself. Gravitational waves are literal waves in space and time, and detecting them is like hearing space-time ring like a bell, responding to violent cosmic events with oscillations that propagate through the universe at light speed. Now, I want to come back to something that might still be bothering you. I've been talking about space-time as a single unified thing, and I've explained how space and time mix together, how they're not separate, but they still seem different in important ways. Time has that arrow, that sense of flow. You age through time, but you don't age through space. Events are ordered in time, past to future, but not in space. You can visit the same place at different times, but you can't visit the same time at different places. Or, well, actually, I guess you can. That's just being in two different locations at once, which you can't do either. But the point is, time feels special. How do we reconcile that with the idea that space and time are the same? The answer, I think, is that they are the same in their fundamental nature, in that they're both dimensions of space-time, but they play different roles in the structure of physical law because of that mathematical signature difference. That minus sign in the metric, in the formula for distances in space-time, it's not arbitrary. It's fundamental to the causal structure of the universe. It's what makes time different from space in terms of causality, in terms of which events can influence which other events. And that difference, while it's just a difference in a mathematical sign, has profound physical consequences. It creates the distinction between time-like and space-like directions, between motion through time and motion through space, between causality and mere spatial separation. So in a sense, time is special, but not because it's a different kind of thing from space. It's special because it's oriented differently in the geometry of space-time. It's like if you're walking on a hillside, uphill and rightward are both directions, both dimensions of the surface you're walking on, but they feel different because one is aligned with gravity and one isn't. Uphill is harder than rightward, not because uphill is a fundamentally different dimension, but because of how that dimension relates to the force of gravity. Similarly, time is different from space, not because it's a different kind of dimension, but because of how it relates to the causal structure of the universe, to the light cone structure, to the fact that there's a maximum speed for cause and effect. And this brings us to another deep question. Why does space-time have this structure? Why 4 dimensions, 3 of space and 1 of time, with this particular signature? Why not 5 dimensions, or 2, or some other configuration? And honestly, we don't have a complete answer to that. It's one of the big unsolved questions in physics. Some theories, like string theory, suggest there might be extra dimensions beyond the 4 we experience, but they're curled up, compactified, too small to notice in everyday life. Others, like loop quantum gravity, try to derive the structure of space-time from more fundamental principles. But we don't yet have a fully satisfactory explanation for why space-time is the way it is. What we do know is that the structure we observe, 4-dimensional space-time with its particular properties, is remarkably fine-tuned for the existence of complex structures like stars, planets, and life. In a universe with different dimensionality or different signature, physics would be very different. Orbits wouldn't be stable, atoms might not form, the laws of physics might not allow for the kind of complexity we see around us. Whether this is just a lucky coincidence, or whether there's some deeper principle at work, some anthropic reasoning or multiverse explanation, we don't know. It's an open question. But let's think about the implications of all this for our understanding of reality. If space and time are the same thing, if they're unified into space-time, then what does that tell us about the nature of existence? Well, for one thing, it tells us that location in time is just as real, just as physical as location in space. When something happens is as much a part of its identity as where it happens. Events, rather than objects, become the fundamental entities. An object is really a world line, a path through space-time, a continuous sequence of events. You are not a thing that exists at a single moment. You are a 4-dimensional structure, a world line extending from your birth to your death, a worm-like entity in space-time. This is sometimes called the eternalist view or the block universe view, which I mentioned earlier. And it has some strange consequences. If you're a 4-dimensional structure in space-time, then all moments of your life exist equally. Your childhood self exists in space-time just as much as your present self. Your future self exists too, assuming you have a future, which presumably you do. You're not changing from one moment to the next. You're a static structure in space-time, containing all moments of your existence. What we call the passage of time, the feeling that you're moving from past to future, that's not movement through space-time. It's something else, maybe something about consciousness, about how we experience the structure of space-time from within. And this raises profound philosophical questions. If all moments exist equally, then in what sense is the present special? Why do we experience this moment as now and not some other moment? Why do we remember the past and not the future? These questions don't have easy answers, and different philosophers and physicists have different views. Some think consciousness is the key, that the present is special because it's the moment we're conscious of, and that consciousness is something that moves through space-time, creating the experience of flow even though the underlying space-time is static. Others think the present isn't special at all, that it's just an arbitrary label for whatever moment we're experiencing, and that every moment feels like now to the version of you at that moment? I don't have a definitive answer to these questions. Nobody does. But I think it's important to recognize that our understanding of space and time as unified space-time, while it's solidly grounded in physics and experiment, does challenge some of our intuitions about existence, about consciousness, about the nature of reality. It suggests that time is not what it seems, that the flow we experience is not a fundamental feature of the universe, but rather something about our perspective, our experience, our place within space-time. And there's another aspect to this that's worth considering. If space-time is fundamental, if it's a real physical thing, then what happens at the quantum level? Because quantum mechanics, our theory of the very small, is strange in its own right. And combining quantum mechanics with general relativity, with the geometry of space-time, has been one of the great challenges of theoretical physics for nearly a century. We have quantum field theory, which combines quantum mechanics with special relativity, and that works beautifully. It's the most precisely tested theory in all of science. But combining quantum mechanics with general relativity with curved space-time has proven incredibly difficult. The problem is that in quantum mechanics, everything is probabilistic, uncertain, described by wave functions that give probabilities for different outcomes. But in general relativity, space-time is a definite classical geometry. Massive objects curve space-time, and that curvature determines how things move. But what if the object is a quantum object, described by a wave function that's in a superposition of different positions? Does it curve space-time in multiple different ways at once? Does space-time itself become quantum, uncertain, probabilistic? And if so, what does that even mean? We don't have a complete theory of quantum gravity yet. There are candidate theories, string theory and loop quantum gravity being the most well-known, but none of them are fully developed or tested. What we do know is that at very small scales, the Planck scale, about 10 to the minus 35 meters and 10 to the minus 43 seconds, quantum effects become important for space-time itself. At those scales, space-time might not be smooth and continuous. It might be foamy, fluctuating, uncertain. The very notion of a definite geometry might break down. Space and time might emerge from something more fundamental, something that doesn't have a clear spatial or temporal character. Some theorists think space-time is emergent, that it's not fundamental, but rather arises from some deeper quantum structure, some network of relationships between quantum bits of information. In this view, space and time as we know them are like temperature or pressure, macroscopic properties that emerge from the collective behavior of many microscopic constituents, but don't exist at the microscopic level. Just as temperature is the average kinetic energy of many particles and doesn't apply to a single particle, maybe space-time is a large-scale structure that emerges from some quantum substrate but doesn't exist at the Planck scale. This is speculative, of course. We don't know if it's true, but it's an active area of research, and it raises fascinating questions about the ultimate nature of space and time. If they're emergent, then the unity of space and time, the fact that they're aspects of space-time, might be a feature of the emergent description, but not of the fundamental reality. Or maybe the fundamental reality is even more unified, even more deeply interconnected than space-time, something where the distinctions between space, time, matter, and energy all dissolve into a single quantum structure. But even if space-time is emergent, even if it's not the deepest level of reality, at the scales we live at the scales where classical general relativity applies, space and time are definitely unified. They're definitely aspects of the same thing. And that's not just a theoretical idea. It's tested, confirmed, used in technology, observed in the universe. It's how reality works, at least at the scales we can measure. There's something else I want to mention, something that might help make all this more concrete. One of the best ways to visualize space-time is through space-time diagrams. These are graphs where one axis represents space and another represents time, and you can plot the paths of objects through space-time as curves on the diagram. These paths are called world lines. A stationary object has a vertical world line, moving only through time. A moving object has a tilted world line, moving through both space and time. Light moves at a 45-degree angle if you choose units where the speed of light is 1, because light moves equal amounts through space and time. On these diagrams, you can see how different observers moving relative to each other have different definitions of what's simultaneous, different slices through space-time that they call now, and you can see the light cones, the regions of space-time that can causally affect or be affected by a given event. The whole structure of space-time, the mixing of space and time, the relativity of simultaneity, it all becomes much clearer when you visualize it on a space-time diagram. If you've never seen one, I'd recommend looking it up. It's one of those things that's hard to describe in words but becomes obvious when you see the picture. And these diagrams also make clear that space-time is not Euclidean. It doesn't have the geometry of ordinary flat space. It has a different geometry, Minkowski geometry in special relativity, or more complicated curved geometries in general relativity. And that non-Euclidean geometry is essential. It's what makes time different from space, what creates the light cone structure, what allows for relativity and causality, and all the strange effects we've been discussing. If space-time were Euclidean, if space and time mixed together in the same way that different space dimensions mix, then time would be just another space direction. And we wouldn't have the arrow of time, wouldn't have causality, wouldn't have the universe we observe. So the unity of space and time isn't a simple merging where they become indistinguishable. It's a sophisticated unity where they're aspects of a single structure with a particular geometry, a geometry that has profound physical consequences. They're the same thing in the sense that they're both dimensions of space-time, but they're different in how they contribute to the geometry of space-time. And that difference is what makes the universe causal, what gives time its special role, what creates the distinction between past and future. Let me try to tie all this together to bring it back to the question we started with. Why are space and time the same thing? The answer ultimately is that they're the same thing, because that's how the universe is structured. The fundamental entity is space-time, not space and time separately. Space and time are not independent, not absolute, not separate aspects of reality. They're coordinates, reference frames, ways of slicing up space-time that depend on who's doing the slicing. Different observers moving relative to each other slice space-time differently, disagree about what's space and what's time, but all observers agree on space-time, on the underlying four-dimensional structure. This isn't just a matter of perspective or convenience. It's not that we could describe things using space and time separately if we wanted to, but find it easier to use space-time. It's that space and time separately don't have objective existence. There's no fact of the matter about how much time elapses between two events or how far apart they are in space without specifying a frame of reference, a state of motion. But there is a fact of the matter about the space-time interval between them, the invariant quantity that all observers agree on. Space-time is real. Space and time as separate entities are not. And this has been confirmed over and over again by experiment and observation. Every test of relativity, every measurement of time dilation or length contraction, or gravitational redshift or gravitational waves confirms that space-time is the right way to describe reality. We don't live in a universe with space and time, we live in a universe with space-time. And once you accept that, once you internalize it, it changes how you think about everything. Motion through space is motion through space-time. Events don't happen in space at a time. They happen at a point in space-time. The history of the universe is not a sequence of spatial configurations evolving over time. It's a four-dimensional space-time geometry, a fixed structure containing all events. This can be disconcerting, even disturbing. It challenges our intuitions, our sense that the present is special, that the past is gone, and the future doesn't exist yet. But that's what the evidence tells us. That's what the mathematics says. That's what experiments confirm. Space and time are the same thing, not in every respect, not in a way that erases all distinctions, but in the deep sense that they're both dimensions of a unified four-dimensional space-time, and that space-time is the fundamental reality. And maybe there's something beautiful about that. Maybe there's something profound and elegant in the idea that the universe is not three dimensions evolving over time, but four dimensions existing as a complete structure. Maybe the unity of space and time tells us something about the nature of existence, about the coherence and interconnectedness of reality. We're not separate from the universe, not observers outside space-time looking in. We're part of space-time, woven into its fabric, our world lines threading through its geometry. Every moment of our existence is a point in space-time, and all those points together form the structure that we are. There's a kind of comfort in that, I think. The idea that everything that happens, every moment, every experience is preserved in space-time is a real part of the structure of reality, never truly lost or gone. The past doesn't cease to exist. It's still there, in space-time, just as real as the present. And the future is there too, in some sense, though what exactly that means for free will and determinism is, as I said, a deep philosophical question without easy answers. But the unity of space and time, the existence of space-time as a single coherent structure, suggests a kind of completeness, a wholeness to reality that's different from the picture of a universe constantly becoming, constantly changing, with only the present moment truly real. Of course, this raises as many questions as it answers. What is consciousness if all moments exist equally? What is the present if it's not ontologically special? How do we reconcile our subjective experience of time flowing with the block universe picture? These are hard questions, and I don't pretend to have answers. But I think they're worth asking, worth thinking about, because they get at something fundamental about the relationship between physics and experience, between the objective structure of the universe and our subjective understanding of it. And there's still so much we don't know. We don't know if space-time is fundamental or emergent. We don't know how to combine general relativity with quantum mechanics into a complete theory of quantum gravity. We don't know why space-time has the dimensionality and signature it has. We don't know if there are other universes with different space-times, different laws. We don't know what happened at the Big Bang or what will happen at the end of the universe. We don't fully understand black holes or dark energy or the ultimate fate of space-time itself. But what we do know, what we've learned from Einstein and Minkowski and all the physicists who've built on their work, is that space and time are not what we thought they were. They're not separate, not absolute, not independent. They're aspects of space-time, dimensions of a unified structure, coordinates that mix and change depending on motion. This is one of the great triumphs of 20th century physics, one of the deepest insights we've gained about the nature of reality. And it's not just abstract theory, it's confirmed by experiment, used in technology, observed in the cosmos. It's true as best as we can tell, and it fundamentally changes how we understand the universe. So when someone asks why space and time are the same thing, the answer is because that's what the universe is. Space-time, not space and time, but space-time, a single unified four-dimensional entity with a particular geometry, a geometry that determines causality, that allows for motion and change, that curves in response to mass and energy, that ripples with gravitational waves, that began with the Big Bang and will end perhaps in heat death or big crunch or some other cosmic finale we can barely imagine. Space and time are the same thing because there is no space without time, no time without space, only space-time, the fundamental stage on which all of existence unfolds. And we are part of that stage, participants in its geometry, our world lines etched into its fabric, part of the vast, interconnected, four-dimensional whole that is the universe. That's what physics tells us. That's what the evidence shows. And that, I think, is one of the most profound and beautiful truths we've ever discovered. Now, let's move on to another theory for you to reflect on. I've been thinking about stars lately, and it's strange, because we see them every night, these little points of light scattered across the darkness, and they seem so simple, so permanent, so unchanging. We look up, and there they are, the same constellations our ancestors saw thousands of years ago. And there's something comforting in that, something that makes us feel like at least some things in this universe are eternal, fixed, reliable. But that's not true at all, not even close. Stars are born, they live, they die. They have life cycles just like we do, just like everything else in this cosmos, and their lives are so much more violent, so much more dramatic, so much more consequential than we ever imagined when we were just looking up at those little pinpricks of light. And when you really start to understand what's happening up there, when you dig into the science of stellar birth and death, what you find is this incredible story, this epic tale of creation and destruction that's been playing out for billions of years. And it's a story that, well, it's intimately connected to us, to you and me, sitting here having this conversation, because we wouldn't exist without it. The thing is, stars aren't just pretty lights in the sky. They're not just distant suns scattered across space. They're furnaces, massive nuclear reactors fusing atoms together, creating the very elements that make up, well, everything. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was forged inside stars that lived and died billions of years ago. Carl Sagan said it best, didn't he? We are made of star stuff. And that's not just poetic language, not just a nice metaphor to make us feel connected to the cosmos. It's literally true. Every atom in your body, except for hydrogen and some helium, was created in the nuclear furnace of a star, or in the violent explosion when that star died. So when we talk about the birth and death of stars, we're not just talking about some distant astronomical phenomenon. We're talking about the very origin of matter itself, the creation of the elements, the story of how the universe became complex enough to produce planets and life and consciousness. But let's start at the beginning, right? Let's start with what a star actually is, because even the basic definition is more interesting than you might think. You might say, well, a star is a big ball of hot gas. And yeah, that's true in the simplest sense, but it's not really capturing what makes a star a star. See, there are lots of big balls of gas out there in space. Jupiter is a big ball of gas. There are clouds of gas between the stars that are bigger than entire solar systems. What makes a star different, what makes it special, is that it's massive enough, dense enough, hot enough at its core that hydrogen atoms are being fused together into helium. And that process, that nuclear fusion, releases enormous amounts of energy. That's what makes a star shine. That's what makes it a star, rather than just a ball of gas. It's not burning in the way a fire burns, it's not chemical combustion. It's nuclear fusion, the same process that powers hydrogen bombs, but it's happening in a controlled, sustained way, and it's been happening inside our sun for about 4.6 billion years, and it'll keep happening for another 5 billion or so. And that's remarkable when you think about it. The sun has been doing this for billions of years. Every second right now as we're talking, the sun is converting about 600 million tons of hydrogen into helium, 600 million tons every second. And in that process, about 4 million tons of matter are being converted directly into energy, pure energy, according to Einstein's famous equation, E equals mc squared. 4 million tons of matter just becomes energy, and that energy radiates outward. And 8 minutes later, some of it reaches Earth, and it warms your face. It makes plants grow. It powers the weather. It makes life possible. That's what's happening right now, has been happening every second of every day, since long before humans existed, since long before Earth existed even, and it'll keep happening long after we're gone. There's something both humbling and awe-inspiring about that, isn't there? But stars don't just exist. They're not eternal, even though they seem that way on human timescales. They have to come from somewhere. They have to be born. And understanding how stars are born, well, that took us a long time to figure out. For most of human history, stars were thought to be eternal, unchanging, fixed to a crystal sphere that rotated around the Earth. Then we figured out they were distant suns, and we started to wonder, how did they get there? How did our sun form? Where do stars come from? The answer, it turns out, is from clouds. Giant molecular clouds, astronomers call them, these vast regions of space filled with gas and dust, mostly hydrogen with some helium and traces of heavier elements. And these clouds are cold, really cold, just a few degrees above absolute zero, and they're incredibly diffuse, much thinner than the best vacuum we can create on Earth, but they're enormous, hundreds of light years across. And they contain enough material to make thousands or even millions of stars. And these clouds are where stars are born, in stellar nurseries. And the process is beautiful and complex. And, well, it's still not completely understood even today, even with all our telescopes and computer simulations. Here's how it works, or at least how we think it works. You've got this giant cloud of gas and dust floating in space. And for the most part, it's just sitting there, not doing much, maybe slowly rotating, maybe being pushed around a bit by stellar winds from nearby stars, or by the pressure of starlight. But then something happens, some disturbance. Maybe a nearby star explodes in a supernova and the shock wave hits the cloud, or maybe the cloud passes through a region where it gets compressed, or maybe it just accumulates enough mass that parts of it start to collapse under their own gravity. And that's the key thing. That's what starts the whole process. Gravity. See, even in this incredibly diffuse cloud, every particle of gas is pulling on every other particle through gravity. And normally the cloud is held up by its own internal pressure, by the motion of the gas molecules. But if some region of the cloud gets a little denser, a little colder, then gravity can start to win. The denser region pulls in more gas, which makes it denser still, which makes its gravity stronger, and you get this runaway process where the cloud fragments into smaller clumps, and these clumps start to collapse. And as they collapse, they spin faster, just like a figure skater pulling in their arms, and they heat up because gravitational potential energy is being converted into thermal energy, into heat, and at the center of each collapsing clump, you start to get a protostar forming. And this is where it gets really interesting, because this protostar, it's not a star yet, not quite. It's glowing because it's hot, because of all that gravitational compression. But it's not doing fusion yet. It's just getting hotter and denser and more compressed as more material falls onto it from the surrounding cloud. And this process, this collapse, it doesn't take that long actually, not on astronomical timescales. For a star like our Sun, the collapse from cloud to protostar takes maybe 100,000 years, which sounds like a long time, but in cosmic terms, it's the blink of an eye. And around the protostar, the material that's falling in doesn't just fall straight down, it forms a disk, a protoplanetary disk, spinning around the forming star. And that's where planets will eventually form, but we're getting ahead of ourselves. The protostar keeps contracting, keeps getting hotter at its core, and eventually, if it's massive enough, the temperature and pressure at the center reach a critical threshold. The core gets to about 10 million degrees Celsius, and at that temperature, hydrogen nuclei, which are just protons, are moving so fast with so much energy that when they collide, they can overcome the electromagnetic repulsion between them, because they're both positively charged and like charges repel, and they can get close enough for the strong nuclear force to take over and bind them together. And when that happens, when hydrogen fusion ignites in the core, that's when the protostar becomes a true star. That's its birth, in a sense. The star stops contracting because now there's an energy source at the core, this nuclear furnace, and the outward pressure from that energy balances the inward pull of gravity. And the star settles into a stable configuration where it can stay for millions or billions of years. And that's what our Sun is doing right now, right? It's in this stable phase, what astronomers call the main sequence. And it's been on the main sequence for about 4.6 billion years. And it'll stay there for another 5 billion or so, just steadily fusing hydrogen into helium in its core, shining steadily, providing the energy that makes life on Earth possible. And most stars spend most of their lives in this phase on the main sequence, just steadily burning hydrogen. And that's why when we look at stars in the sky, most of them are main sequence stars, because that's where stars spend most of their time. But here's the thing, and this is crucial to understanding stellar death. Not all stars are created equal. Not all stars are the same mass. And mass, it turns out, is destiny when it comes to stars. A star's mass determines almost everything about its life. How long it lives, how hot it burns, what color it is, and most importantly, how it dies. Small stars, red dwarfs, stars that are maybe a tenth or a fifth the mass of the Sun, they burn their hydrogen very slowly, very efficiently, and they can live for trillions of years, far longer than the current age of the universe. We've never actually seen a red dwarf die because the universe isn't old enough yet for any of them to have run out of fuel. On the other end of the scale, you have massive stars, blue giants, stars that are 10 times, 20 times, 50 times the mass of the Sun, and these stars burn through their hydrogen incredibly fast, and they live fast and die young. A star that's 30 times the mass of the Sun might only live a few million years before it runs out of fuel and dies in a spectacular explosion. So mass is everything. Our Sun is right in the middle. It's a medium-sized star, and it'll have a medium sort of death, not too dramatic, not too subtle, and we can use it as an example to understand what happens when a star like the Sun dies, because that's what we're really interested in, isn't it? The death of stars, the end of these titanic nuclear furnaces. And the death of a star, it's not a simple thing. It's not just the star running out of fuel and winking out like a candle. It's a complex multi-stage process that can take millions of years, and it completely transforms the star, and it has profound consequences for the surrounding space. So let's imagine we're watching the sun, but we can speed up time. We can watch it evolve over billions of years in the space of a few minutes. For the first 4.5 billion years, not much changes. The sun is on the main sequence, fusing hydrogen in its core, shining steadily. But then, about 10 billion years into its life, something starts to happen. The hydrogen in the core starts to run out. See, the fusion process only happens in the very center of the star, where it's hot enough and dense enough, and gradually, over billions of years, the hydrogen there gets converted into helium, and helium accumulates in the core, and helium doesn't fuse at these temperatures. It just sits there inert, building up. And when the hydrogen in the core is exhausted, fusion stops, at least in the core. And without fusion producing energy, there's nothing to hold up the core against gravity, so the core starts to contract. And as it contracts, it heats up, because gravitational contraction releases energy, and the temperature of the core goes up, and the region just outside the core, where there's still hydrogen, gets hot enough to start fusing. So now you have fusion happening in a shell around the inert helium core, and this is called hydrogen shell burning. And here's the weird thing. When this happens, the star doesn't stay the same size. You might think, okay, fusion is still happening just in a shell instead of the core, so the star should be fine, right? But no. The energy output actually increases, and the outer layers of the star expand, dramatically expand, and the star grows larger and larger. And as it expands, its surface cools down because the same energy is being spread over a much larger area. And cooler surfaces emit red light rather than yellow or white, so the star becomes a red giant. And when I say the sun will expand, I mean really expand. It'll grow to maybe 100 times its current diameter, maybe more. It'll swallow Mercury, probably Venus, and it might reach Earth's orbit or come close to it. The sun, our familiar yellow star, will become this enormous red giant, bloated and cool on the surface, but incredibly luminous because of its sheer size. And this phase, this red giant phase, it doesn't last as long as the main sequence, maybe 1 billion years or so. And during this time, the helium core keeps contracting and heating up. And eventually, if the star is massive enough and the sun is just barely massive enough, the core reaches about 100 million degrees. And at that temperature, helium can start to fuse. And when helium fusion ignites, it doesn't happen gradually. In stars like the sun, it happens all at once in what's called the helium flash, this sudden runaway fusion reaction where the entire core ignites in a matter of seconds, releasing an incredible amount of energy. But this energy is absorbed by the outer layers of the star, so we don't see it from the outside. The star actually settles down a bit, shrinks a little, becomes a bit more stable, and enters another phase where it's fusing helium in the core and hydrogen in a shell around the core, and it can stay like this for maybe 100 million years. But helium burning doesn't last as long as hydrogen burning because helium fusion releases less energy per reaction, and eventually the helium in the core runs out too, and you're left with a carbon and oxygen core, and the whole process starts to repeat. But here's the thing, for a star like the sun, this is as far as it goes. The core isn't massive enough, isn't hot enough to fuse carbon and oxygen into heavier elements. The temperature would need to be billions of degrees, and a sun-sized star just can't get there. So what happens instead is that the outer layers of the star become increasingly unstable. The star goes through these pulses, these thermal pulses, where fusion in the shells around the core flares up and dies down, flares up and dies down, and these pulses drive strong stellar winds that blow the outer layers of the star away into space, creating these beautiful structures called planetary nebulae, which is kind of a misleading name because they have nothing to do with planets. They're called that because through early telescopes they looked kind of round and disc-like, like planets, but really they're just the expanding outer layers of the dying star, glowing because they're being lit up by the hot core at the center. And that core, that carbon-oxygen core left behind, it's no longer generating energy through fusion. It's just sitting there, incredibly hot, incredibly dense, supported now not by thermal pressure, but by something called electron degeneracy pressure, which is a quantum mechanical effect. It's about the size of Earth, but it has about half the mass of the sun packed into that small volume, and we call it a white dwarf. And this white dwarf will just sit there, slowly cooling off, radiating its stored heat into space over billions and billions of years, eventually becoming a black dwarf, though the universe isn't old enough yet for any white dwarfs to have cooled down completely to that state. And that's the death of a sun-like star. Not a bang, but a whimper, you might say. The outer layers dispersed into a beautiful nebula, the core left behind as a slowly cooling ember. And this will happen to our sun in about 5 billion years, though by that point, if humans still exist, we'll have had to leave Earth long before during the red giant phase, because Earth will be uninhabitable. But that's for stars like the sun. For more massive stars, stars with more than about 8 times the mass of the sun, things are very, very different. See, massive stars have enough mass, enough gravitational pressure to fuse not just hydrogen and helium, but carbon, oxygen, neon, magnesium, silicon, all the way up to iron. And they do this in stages, in layers, like an onion. After they finish fusing hydrogen to helium, they contract and heat up until they can fuse helium to carbon. Then they contract and heat up more until they can fuse carbon to neon and magnesium, then oxygen to silicon, then silicon to iron. And each stage happens faster than the last because each fusion process releases less energy per reaction, and the star has to burn through it faster to maintain equilibrium against gravity. A massive star might spend millions of years fusing hydrogen, a few 100,000 years fusing helium, a few thousand years fusing carbon, a few years fusing oxygen, and only a few days fusing silicon into iron. And then suddenly, catastrophically, it stops. Because iron is the end of the line. Iron is the most stable nucleus, the most tightly bound, and fusing iron doesn't release energy, it requires energy. So when the core of a massive star turns to iron, fusion stops. There's no more energy being generated and nothing to hold up the core against the crushing force of gravity from all the mass above it. And what happens next happens fast, incredibly fast. The iron core collapses. In less than a second, a core with the mass of the sun, about the size of Earth, collapses down to about 10 kilometers across. 10 kilometers. The density becomes unimaginable, higher than the density of an atomic nucleus. Electrons are forced into protons, creating neutrons, and the core becomes essentially a giant atomic nucleus made of neutrons, a neutron star. And the collapse releases an enormous amount of gravitational potential energy, more energy than the star has emitted in its entire life up to that point. And this energy blows apart the rest of the star in what we call a supernova, one of the most energetic events in the universe. A supernova, for a brief time, can outshine an entire galaxy. Think about that. One star in its death throes can briefly emit more light than 100 billion other stars combined. It's visible across the universe. The brightness increases over a few days or weeks, and then slowly fades over months or years. And in that explosion, something incredible happens. The extreme temperatures and pressures create conditions where fusion can happen, not just of hydrogen and helium and the lighter elements, but of heavy elements, elements heavier than iron, things like gold and silver and platinum and uranium. These elements can't be made in normal stellar fusion because they require more energy than they release. But in a supernova, there's so much energy available that these elements can be synthesized and they're thrown out into space along with all the lighter elements that were made during the star's life. And this is where we come back to that idea of being made of star stuff, because all the heavy elements in the universe, everything heavier than hydrogen and helium, most of it was made inside stars and then scattered into space when those stars died, either gently as planetary nebulae or violently as supernovae. The iron in your blood was made in the core of a massive star billions of years ago, fused from lighter elements and then thrown into space when that star exploded. The oxygen you breathe was made in a star. The carbon that forms the basis of all organic chemistry, of DNA and proteins and everything that makes life possible, was made in a star. The gold in jewelry, the silver in coins, the uranium in nuclear reactors, all of it made in supernovae or in even more exotic events like the collisions of neutron stars. So stars aren't just pretty lights in the sky, and their deaths aren't just interesting astronomical phenomena. Stellar death is the mechanism by which the universe creates complexity, creates the periodic table, creates the elements necessary for planets and life and everything interesting. The early universe, just after the Big Bang, was almost entirely hydrogen and helium, the simplest elements. created in the first few minutes after the Big Bang. Everything else, all the complexity, all the diversity of the periodic table that was created in stars, the universe had to make a generation of stars, and those stars had to live and die, scattering their processed material into space, and then that material had to form a second generation of stars with planets around them, before you could have planets like Earth with rock and metal and water and all the ingredients for life. We are literally the children of stars, multiple generations of stars, and we exist only because of the death of stars. And the neutron star left behind by a supernova, that's an object so strange, so extreme, that it's hard to comprehend. A neutron star has about 1.4 times the mass of the Sun, but it's only about 20 kilometers across, 10 kilometers radius. If you could put a neutron star next to Earth, it would be smaller than a large city, but it would contain more mass than the Sun. The density is, it's absurd. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is so strong that if you somehow stood on a neutron star, you would be flattened to a thickness of a few atoms. And that's assuming you didn't immediately ignite into plasma from the extreme conditions. The escape velocity at the surface is about half the speed of light. And neutron stars do something remarkable. They spin fast, really, really fast. See, when the core collapses, conservation of angular momentum means that the spin rate increases dramatically, just like that figure skater pulling in their arms. And neutron stars can rotate hundreds of times per second. And if the neutron star has a strong magnetic field, which many do, then that field gets wound up and concentrated during the collapse, and it can produce beams of radiation from the magnetic poles. And as the neutron star spins, these beams sweep around like a lighthouse. And if one of those beams happens to point toward Earth, we see a pulse of radiation every time it rotates, and we call these objects pulsars. And when pulsars were first discovered in 1967 by Jocelyn Bell Burnell, the pulses were so regular, so precise, that for a brief moment, astronomers thought they might be signals from an alien civilization. They even nicknamed the first one LGM1 for Little Green Men. But of course, they turned out to be natural phenomena, these incredibly dense, rapidly spinning remnants of dead stars. But there's one more possibility for the death of a star, one more fate for the most massive stars, and this is the most extreme, the most bizarre, the most fascinating: black holes. If a star is massive enough, if the core left behind after a supernova is more than about 3 times the mass of the Sun, then not even neutron degeneracy pressure can hold it up against gravity. Nothing can. The core collapses completely, collapses beyond the neutron star stage, collapses until it becomes infinitely dense, or at least that's what the mathematics says, though we're not sure if that's actually true because our physics breaks down at those extremes. What we do know is that the gravity becomes so strong that not even light can escape, and a region of space-time forms from which nothing, absolutely nothing, can escape once it crosses a boundary called the event horizon. We call these objects black holes, and black holes are strange, really strange. They're not holes in space, despite the name. They're regions where gravity is so strong that space-time itself is warped beyond our ability to intuit it. Time slows down near a black hole, relative to an outside observer, and at the event horizon, time effectively stops from the perspective of someone far away. If you watch someone fall into a black hole, you would see them slow down as they approach the event horizon, their image getting redder and dimmer, and you would never quite see them cross it, though from their perspective they would cross it and fall in just fine, though they wouldn't survive the experience because the tidal forces, the difference in gravitational pull between their head and their feet, would tear them apart long before they reached the horizon, a process gruesomely called spaghettification. And what's inside a black hole? What happens at the center, at what's called the singularity? Honestly, we don't know. The mathematics of general relativity predicts a singularity, a point of infinite density, but most physicists suspect that this is a sign that our theory breaks down there, that we need a theory of quantum gravity to understand what really happens at those scales. Maybe the singularity is a real thing, maybe it's not. Maybe there's some exotic form of matter at the center. Maybe the inside of a black hole is connected to another universe. Maybe. We don't know. It's one of the great unsolved mysteries. But what we do know is that black holes exist. We've detected them in multiple ways. We've observed stars orbiting around invisible massive objects at the centers of galaxies, including our own Milky Way, which has a supermassive black hole called Sagittarius, a star at its center, with a mass of about 4 million suns. We've detected gravitational waves, ripples in space-time itself, produced when black holes collide and merge, something that LIGO, the Laser Interferometer Gravitational Wave Observatory, first detected in 2015, a discovery that earned the Nobel Prize because it confirmed a century-old prediction of Einstein's general relativity. And in 2019, the Event Horizon Telescope collaboration released the first actual image of a black hole, or rather, the shadow of a black hole, against the bright material swirling around it, in the center of the galaxy M87. And that image, that blurry orange ring against a black center, was the first direct visual evidence of an event horizon. And it was breathtaking, seeing for the first time something that was long thought to be impossible to observe directly. And supermassive black holes, the ones at the centers of galaxies, they play a crucial role in how galaxies evolve. They can have billions or even tens of billions of times the mass of the sun, and they're not formed from stellar collapse, at least not directly. We think they grow over time by accreting material and by merging with other black holes when galaxies collide, but we're not entirely sure how the first supermassive black holes formed in the early universe, because they seem to exist very early on, only a few 100 million years after the Big Bang, and that's not much time for them to grow to such enormous sizes through accretion alone. It's an active area of research. But let's zoom back out a bit. Let's think about the big picture, because we've been talking about individual stars, but the universe is full of stars, hundreds of billions in our galaxy alone, and hundreds of billions of galaxies in the observable universe, and stars are being born and dying all the time. And the cycle continues, this great cosmic recycling where stars are made from gas clouds. They fuse hydrogen into heavier elements. They die and scatter those elements back into space, and new stars and planets form from that enriched material, and those stars live and die and enrich the material further, and the cycle repeats. And the beautiful thing, the profound thing, is that this process is directional, it's cumulative. The universe started with just hydrogen and helium, and over billions of years, through countless stellar lifetimes, it's created all the elements, all the complexity, and the material keeps getting enriched. Our sun is a third-generation star, or maybe fourth generation, formed from material that had already been through multiple cycles of stellar birth and death. And that's why Earth has rocky planets with iron cores and silicon crusts. And it's why life was possible, because the elements necessary for life, carbon and nitrogen and oxygen and phosphorus and sulfur, all of that was made in previous generations of stars. And there's something deeply moving about this, isn't there? About the fact that the atoms in your body were once inside stars, that they were forged in nuclear furnaces billions of years ago, that you are, in the most literal sense, made of the remnants of stellar death. When you look up at the night sky, you're not just seeing distant objects, you're seeing your relatives, in a sense, your ancestors. The stars that died to make the atoms in your body might have looked similar to the ones you can see now, and new stars are forming right now that will live and die and create the elements that will, billions of years from now, become part of other worlds, other beings perhaps, other consciousnesses, looking up at their night sky and wondering about the stars. And the timescales involved, they're so vast, so hard to really comprehend. The universe is about 13.8 billion years old, and the first stars formed maybe 100 or 200 million years after the Big Bang. And those first stars, the so-called population 3 stars, they were different from the stars we see today. They were massive, probably much more massive on average than today's stars, because they formed from primordial hydrogen and helium with no heavier elements to help cool the gas clouds and allow smaller fragments to collapse. These first stars were probably short-lived, burning bright and hot and dying in supernovae after only a few million years. And those first supernovae scattered the first heavy elements into space, seeding the universe with the first carbon, the first oxygen, the first iron, and allowing the formation of the next generation of stars, which could be smaller and longer lived. And star formation has changed over cosmic time. In the early universe, when there was more gas available, star formation rates were much higher. Galaxies were forming stars at prodigious rates, creating hundreds or even thousands of solar masses worth of stars per year. Today in the Milky Way, the star formation rate is only about 1 or 2 solar masses per year. The universe is running out of easily accessible gas, and star formation is declining, and eventually, in the far future, tens or hundreds of billions of years from now, star formation will cease entirely. All the available gas will have been used up, locked into stars or planetary systems, or expelled from galaxies by active galactic nuclei, and no new stars will form. And then, slowly, over timescales that make the current age of the universe seem like nothing, the existing stars will die. The massive stars will go first, as they already are, living fast and dying in a few million years. Medium stars like the Sun will last billions of years, and many of them are still on the main sequence, still young or middle-aged. But the small stars, the red dwarfs, they'll last for trillions of years, and they'll be the last stars shining in a universe that has grown cold and dark. Eventually, the last stars will die, and the universe will enter what's called the degenerate era, an age where the only objects remaining are stellar remnants, white dwarfs, neutron stars, black holes, and perhaps brown dwarfs that never quite made it to full stardom. And even those objects won't last forever. White dwarfs will cool to black dwarfs over timescales of 10 to the 15th years or more, a million billion years. Protons, if they're unstable as some theories suggest, might decay over timescales of 10 to the 34th years, causing even the remnants to slowly dissolve. Black holes will evaporate through Hawking radiation, a quantum mechanical process where particle pairs form at the event horizon and one falls in while the other escapes. And this causes the black hole to slowly lose mass and eventually evaporate entirely, though for a solar mass black hole, this would take about 10 to the 67th power years, and for a supermassive black hole, it could take 10 to the 100th power years or more. So the ultimate fate of the universe, at least in terms of stars, is cold and dark and empty. All the stars will die, all the stellar remnants will decay or evaporate, and the universe will become a vast, empty expanse with nothing left but the faint whisper of radiation, cooled to nearly absolute zero, and no structure, no complexity, no life, just, well, nothing. Or nearly nothing. It's called the heat death of the universe, and it's the eventual end point if the universe continues to expand forever, which current observations suggest it will, and actually the expansion is accelerating due to something we call dark energy, though we don't really understand what dark energy is. But that's tens or hundreds of billions or trillions of years in the future, timescales so vast that they're hard to even conceptualize. For now, the universe is still in what we might call its prime, the stelliferous era, the age of stars, when the universe is full of light and energy and complexity and life. Stars are still being born in stellar nurseries, fusing hydrogen and creating light and heat, and they're still dying gently as white dwarfs or violently as supernovae, scattering the elements they've created into space, and the cycle continues, and it's beautiful. And I think there's something profound about understanding this, about knowing that we live in this brief, bright moment in cosmic history when the universe is full of stars. We exist in a universe that is old enough to have gone through multiple generations of stellar evolution, creating the complex elements necessary for planets and life, but young enough that stars are still shining, still providing energy, still making the universe bright and interesting and complex. It's a remarkable time to be alive, in a sense, a remarkable time in the history of the cosmos. And when you look at it from this perspective, human history, all of recorded human history, it's just a tiny blip, a fraction of the lifetime of even a single star like the Sun. The Sun was already 4.5 billion years old when Earth formed, and it had been shining for all that time, and it'll continue shining for another 5 billion years. And in that grand sweep of time, all of human civilization, from the first cities to the present day, is less than 1,000th of 1% of the Sun's total lifetime. We are ephemeral, fleeting, our lives spanning barely a fraction of even the human era, which itself is barely a flicker in the life of our star. But maybe that makes it more meaningful, not less. Maybe the fact that we exist at all in this brief, bright moment, against all the odds, as improbable collections of atoms forged in the hearts of dying stars billions of years ago, maybe that's what gives life its preciousness, its value. We are the universe becoming aware of itself. In Carl Sagan's words, we are a way for the cosmos to know itself, and that's a remarkable thing. We're not separate from the universe, watching it from the outside. We're part of it, intimately connected to it, made of the same stuff as stars, governed by the same physical laws, participating in the same grand cosmic story. And the story of stellar birth and death, it's not just a story about distant objects in space, it's our story. It's the story of how we came to be, how the elements that make up our bodies were created, how the earth formed, how life became possible. Every breath you take contains oxygen atoms that were once in the core of a star. Every time your heart beats, it's powered by the iron in your hemoglobin, iron that was synthesized in the final moments of a massive star's life and scattered into space in a supernova explosion. The calcium in your bones, the carbon in your DNA, the nitrogen in your proteins, all of it has the same origin. Stellar nucleosynthesis followed by stellar death. And we know this, we understand this. We've figured it out through centuries of scientific investigation, through careful observations and elegant theories and brilliant insights from scientists like Cecilia Payne, who figured out that stars are mostly hydrogen and helium, and Fred Hoyle, who worked out how elements are synthesized in stellar interiors, and Subramanian Chandrasekhar, who calculated the maximum mass of a white dwarf, and Edwin Hubble, who showed us that the universe is full of galaxies and that it's expanding, and so many others who contributed to our understanding of stars and their life cycles. And we're still learning, we're still making new discoveries. The field of stellar astronomy is incredibly active, with new telescopes and new instruments, allowing us to observe stars in unprecedented detail. We can now study individual stars in other galaxies. We can observe the earliest stars that formed after the Big Bang. We can detect the moment when a star begins to explode in a supernova and watch the explosion unfold in real time. We can image the surfaces of stars other than the sun using interferometry. We can detect planets around other stars and study their atmospheres, looking for signs of life. And the questions we're asking now, they're profound. How exactly do the first stars form in the early universe? What triggers star formation in giant molecular clouds? What determines the distribution of stellar masses, what astronomers call the initial mass function? How do massive stars lose so much mass through stellar winds before they explode? What exactly happens inside a supernova in the seconds before and during the explosion? What's at the center of a black hole? How do supermassive black holes form and grow? Are there other mechanisms for creating heavy elements besides supernovae? And how important are events like neutron star mergers in producing things like gold and platinum? And we're developing new tools to answer these questions. The James Webb Space Telescope, launched in 2021, is allowing us to see the earliest galaxies and stars in unprecedented detail, looking back to when the universe was only a few 100 million years old. Gravitational wave observatories like LIGO and Virgo are detecting the collisions of black holes and neutron stars, giving us a completely new way to observe the universe. The Event Horizon Telescope is working on imaging more black holes with higher resolution. New generations of ground-based telescopes, like the extremely large telescope being built in Chile, will allow us to study distant stars and galaxies in exquisite detail. And there's something wonderful about the fact that we can do this, that we can use our intelligence and our technology to understand phenomena that are so far beyond our everyday experience, so far removed from the human scale. We're tiny creatures on a small planet orbiting an average star in an ordinary galaxy. And yet we can understand the physics of objects millions of light years away. We can figure out how stars are born and how they die. We can trace the history of the elements in our bodies back to their origins in stellar furnaces. We can contemplate the far future of the universe billions of years hence. That's extraordinary. And it's worth pausing to appreciate how counterintuitive a lot of this is. How much of stellar physics goes against our everyday intuitions? The fact that stars are held up not by any kind of solid structure, but by a balance between gravity trying to crush them and thermal pressure trying to expand them. That's not obvious. The fact that nuclear fusion can happen at all, that atomic nuclei can overcome their electromagnetic repulsion and merge together, that took quantum mechanics to explain. The fact that gravity can become so strong that it warps space-time and creates black holes from which light cannot escape, that took Einstein's general relativity. And even then, it took decades for physicists to really accept that black holes were real physical objects and not just mathematical curiosities. And some of the predictions are just bizarre. The fact that a white dwarf, which is essentially a ball of carbon and oxygen supported by electron degeneracy pressure, could be the size of Earth but contain half the mass of the Sun. And that if you added more mass to it, it wouldn't get bigger, it would get smaller and denser until it reached a critical point and collapsed, either forming a neutron star or exploding in a Type Ia supernova. The fact that neutron stars can have crusts made of crystallized iron atoms arranged in lattices stronger than any material we can make on Earth, floating on a liquid interior made of superfluid neutrons. The fact that pulsars can rotate hundreds of times per second, a sphere with more mass than the Sun spinning faster than a kitchen blender. It's also strange, so far from anything in our everyday experience. And yet it's real. It's not science fiction, it's science fact. Stars really do work this way. The universe really is this strange and wonderful and complex. And we know this not through speculation or philosophy or religious revelation, but through careful observation and rigorous theory and the scientific method, that incredibly powerful tool we've developed for figuring out how the universe works. We make observations, we develop theories to explain those observations, we make predictions based on those theories, we test those predictions with new observations or experiments, and we refine our theories accordingly. It's a process that's been going on for centuries, and it's given us this incredible body of knowledge about the cosmos. And one of the most profound realizations to come from this is the unity of the universe, the fact that the same physical laws apply everywhere. The nuclear physics that governs fusion in the Sun also governs fusion in a star on the other side of the galaxy or in a galaxy billions of light years away. The gravity that makes things fall on Earth is the same gravity that holds the Moon in orbit, that holds the solar system together, that makes stars collapse and form black holes. The spectroscopy that tells us what elements are in a star's atmosphere works on the same principles as the spectroscopy we use in laboratories on Earth. The universe is comprehensible, it follows rules, and those rules are the same everywhere and as far as we can tell at all times. And this is why we can make such confident statements about stellar evolution, about the birth and death of stars. We're not just speculating, we have detailed theoretical models based on well-understood physics, and we have observations that confirm those models. We can observe stars at different stages of their life cycles, from protostars still forming in their natal clouds, to main sequence stars like the Sun, to red giants, to white dwarfs, neutron stars, and black holes. We can't watch a single star go through its entire life cycle because they live far too long. But we can observe many stars at different stages and piece together the story, like looking at photographs of different people at different ages and figuring out the human life cycle. And we can test our models. For example, the Sun is constantly emitting neutrinos, nearly massless particles that are produced in the fusion reactions in its core. And these neutrinos barely interact with matter, so they stream out of the Sun at the speed of light. And we can detect them here on Earth using massive detectors filled with thousands of tons of water or other materials buried deep underground to shield them from cosmic rays. And the flux of neutrinos we detect, it matches what our models predict the Sun should be producing, which is remarkable because these neutrinos are coming directly from the core of the Sun. They're telling us about the fusion reactions happening right now in the Sun's center. And the fact that our observations match our predictions is strong confirmation that we understand how the Sun works. Or consider Type Ia supernovae, which happen when a white dwarf accretes enough mass from a companion star that it reaches the Chandrasekhar limit, about 1.4 solar masses, and collapses, triggering runaway carbon fusion that destroys the entire star in a thermonuclear explosion. These supernovae are remarkably uniform in their brightness, because they always happen at the same mass, and this makes them incredibly useful as standard candles for measuring distances in the universe. and they were used in the late 1990s to discover that the expansion of the universe is accelerating, a discovery that was so surprising and so important that it earned the Nobel Prize in 2011. So our understanding of stellar death has practical applications for cosmology, for understanding the universe as a whole. And there are still mysteries, of course, still things we don't fully understand. The exact mechanism of core collapse supernovae, for example, is still not completely clear. We know the core collapses and bounces and sends out a shockwave, but the details of how that shockwave is energized and how it manages to blow apart the rest of the star, those details are still being worked out. Computer simulations are getting better and better, and we're starting to understand the role of neutrinos in carrying energy out of the core and reviving the stalled shockwave, but it's a complex, multi-dimensional problem involving general relativity, nuclear physics, neutrino physics, and hydrodynamics, and we're not quite there yet. Or consider stellar rotation. Stars spin, they have angular momentum, and as they evolve, they can lose angular momentum through stellar winds and magnetic braking, and the details of how this works are still being studied. Or the question of how stellar metallicity, the abundance of elements heavier than hydrogen and helium, affects stellar evolution. We know it does. Stars with more metals have different properties and evolve differently, but the details are complex and still being worked out. And then there are the big questions, the really big ones. Why does the universe have stars at all? Why do the physical constants have the values they do, values that allow for stable atoms and nuclear fusion and stars that last for billions of years? If the strength of the strong nuclear force were just a bit different, fusion might not work the way it does, or nuclei might not be stable, and stars as we know them might not exist. If gravity were stronger, stars might burn out too quickly for life to evolve. If it were weaker, stars might never form at all. The universe seems to be fine-tuned for complexity, for structure, for stars and planets and life, and we don't know why. Maybe it's just chance, maybe there are multiple universes with different physical constants, and we happen to be in one where stars are possible because, well, if stars weren't possible, we wouldn't be here to ask the question. That's the anthropic principle, and it's either a profound insight or a tautology, depending on how you look at it. But setting aside these deep philosophical questions, the basic story of stellar birth and death, that's something we understand pretty well. And it's a beautiful story, a story of transformation and recycling and the creation of complexity. Stars are born from clouds of gas and dust. They live for millions or billions of years fusing hydrogen into helium and heavier elements. They die in various ways depending on their mass, and they scatter their processed material back into space where it can form new stars and planets, and the cycle continues. And with each cycle, the universe becomes more rich in heavy elements, more complex, more interesting. And we are part of this cycle. We're made of atoms that were forged in stars. And when we die, those atoms will return to the Earth, and eventually, on timescales of billions of years, they might be incorporated into new stars, new planets, new life perhaps. We're not separate from the cosmos. We're part of its ongoing story, temporary patterns of organization in the flow of matter and energy through space and time. And that brings us back to the question of meaning, doesn't it? If we're just temporary arrangements of atoms, if stars live and die and the universe will eventually grow cold and dark, does anything matter? Does our existence have any significance in the grand scheme of things? These are old questions, philosophical and existential questions that humans have been asking for millennia. And I don't know that understanding stellar evolution gives us definitive answers, but it does give us perspective. One perspective is that we're insignificant, that we're tiny and temporary and ultimately inconsequential in a vast and ancient universe that will continue on for eons after we're gone. And there's some truth to that. We are small and brief. But I think there's another perspective that's equally valid and maybe more meaningful, and that's that the universe has, through us, become aware of itself. We are the way the universe knows about stars, thinks about stars, understands stars. The atoms in your brain, atoms forged in stellar furnaces, are contemplating the processes that created them. That's remarkable. That's not nothing. And maybe meaning isn't something that exists independently. out there in the universe waiting to be discovered. Maybe meaning is something we create, something we give to the universe through our consciousness and our curiosity and our desire to understand. The universe doesn't care whether we exist or not. It doesn't have preferences or intentions. It just is what it is, following the laws of physics, stars being born and dying according to the equations of stellar astrophysics. But we care. We find it meaningful to understand these processes, to contemplate our place in the cosmos, to appreciate the beauty and complexity of it all. And there is beauty in it, isn't there? The image of a stellar nursery, the Orion Nebula or the Eagle Nebula with its pillars of creation, these vast clouds of gas and dust lit up by young stars, with new stars forming inside them. That's beautiful, visually stunning. A planetary nebula like the Ring Nebula or the Helix Nebula, the glowing shell of gas surrounding the dying ember of a star. That's beautiful. The multi-wavelength image of a supernova remnant like the Crab Nebula, the expanding debris of a star that exploded nearly 1,000 years ago, still glowing with high-energy radiation. That's beautiful. These aren't just pretty pictures, they're glimpses into the fundamental processes that shape the universe. And there's an aesthetic dimension to understanding that's hard to articulate, but very real. And there's also a sense of connection, of unity with the cosmos that comes from understanding stellar evolution, when you know that you're made of star stuff. When you know that the calcium in your bones and the iron in your blood were forged in stellar interiors and scattered into space by stellar winds or supernova explosions, when you know that you're literally composed of the ashes of long-dead stars, it's hard not to feel connected to the universe in a deep way. You're not separate from it. You're not just an observer looking at it from the outside. You're part of it, made of the same matter, governed by the same laws, participating in the same grand story of cosmic evolution. And that story is still unfolding. The universe is still full of stars, still full of light and energy and complexity. New stars are being born every day. Massive stars are dying in supernovae. White dwarfs are slowly cooling. Black holes are merging and releasing gravitational waves. And all of this is happening right now as we sit here contemplating it. The universe is not static, it's dynamic, constantly changing, constantly evolving, and we're privileged to exist in an era when we can observe and understand these processes, when we have the technology and the knowledge to peer deep into space and back in time and see stars at various stages of their life cycles, when we can test our theories against observations and refine our understanding. And the knowledge we've gained, it's cumulative. It builds on itself. Each generation of scientists stands on the shoulders of the previous generation, and we know more now about stars than we did 100 years ago and 100 years from now. If we continue this scientific tradition, we'll know even more. There are questions we can't answer yet, mysteries that remain unsolved, but that's okay, that's exciting actually, because it means there's more to learn, more to discover, more opportunities for wonder and insight. And wonder, that sense of awe and fascination and curiosity, that's important. That's part of what makes us human, part of what drives us to explore and understand. When you look up at the night sky and see thousands of stars and you know that each one is a sun, potentially with planets around it, potentially with life, and you know that each one has its own story of birth and evolution and eventual death, and you know that the light you're seeing left those stars years or decades or centuries or even millennia ago because of the finite speed of light. So you're literally looking back in time, seeing these stars as they were in the past. That's awe-inspiring. That's wonderful in the true sense of the word, full of wonder. And maybe that's the point. Maybe the significance of understanding stellar birth and death isn't that it gives us control over the universe or that it serves some practical purpose, though it certainly does inform our understanding of many things, but rather that it enriches our experience of being alive, of being conscious beings in this strange and beautiful universe. It deepens our appreciation, it broadens our perspective, it connects us to something larger than ourselves. So when we talk about the birth and death of stars, we're talking about the most fundamental processes of cosmic evolution, the mechanisms by which the universe creates complexity and diversity, and eventually the conditions for life. We're talking about the origin of the elements, the history written in starlight, the grand cycle of matter and energy that has been going on for billions of years and will continue for billions more. We're talking about our own origins, our connection to the cosmos, the fact that we are quite literally made of star stuff. And the story continues. Stars are being born right now in molecular clouds across the galaxy and across the universe, clouds like the Orion Nebula, which you can see with binoculars or even the naked eye under dark skies, just south of Orion's belt, that fuzzy patch of light that's actually a stellar nursery where thousands of stars are forming. And stars are dying right now. Massive stars running out of fuel and collapsing, exploding in supernovae that briefly outshine entire galaxies, scattering their enriched material into space. And in between, on the main sequence, billions of stars like our Sun are steadily fusing hydrogen, providing stable energy for any planets that might orbit them, possibly including planets with life, with other beings looking up at their own night sky and pondering the same questions we're pondering. And it all comes back to this. We live in a universe governed by natural laws, laws that we can understand through observation and reason. The birth and death of stars isn't random. It's not mysterious in the sense of being unknowable. It follows from the physics of matter and energy, from gravity and thermodynamics and nuclear physics. And yet, even though we understand the mechanisms, even though we can calculate the life expectancy of a star based on its mass and composition, even though we can predict how it will die, there's still something profound and moving about it, something that transcends the equations and speaks to the human experience. Because in the end, stars are like us, in a way. They're born, they live, they die, they transform their surroundings, they create new things, they leave a legacy. When a massive star dies in a supernova, it enriches the interstellar medium with heavy elements, and those elements become part of the next generation of stars and planets. When the sun dies, it will return its processed material to the galaxy, contributing to the ongoing cycle. Nothing is permanent. Everything changes, but the changes are part of a larger pattern, a cosmic cycle of death and rebirth, destruction and creation. And we're part of that pattern. Our atoms were made in stars. They've been through multiple cycles of stellar birth and death, and they'll continue on after we're gone, eventually becoming part of other structures, other stars, perhaps other worlds. We're temporary, but we're connected to something eternal, or at least very long-lasting, this ongoing process of cosmic evolution. And maybe that's enough. Maybe being part of this grand story, being conscious participants in the universe's journey of self-discovery, maybe that's all the meaning we need. So the next time you look up at the night sky, remember what you're seeing. Those aren't just points of light. They're nuclear furnaces, massive balls of plasma fusing atoms together, creating the elements that make up everything, including you. They're at different stages of their lives, some young and hot and blue, some old and cool and red, some dying, some being born. And the light you're seeing, it left those stars years or centuries ago, so you're seeing them as they were in the past. And some of them might have already died. Their light still traveling through space toward us, long after the star itself has gone. And remember that you're made of the same stuff as those stars, that the atoms in your body were once inside stellar cores, undergoing fusion, being transformed from lighter elements into heavier ones, and then scattered into space when those stars died, and then incorporated into the molecular cloud that collapsed to form our solar system, and then into the Earth, and then into living things, and eventually into you. You are stardust, quite literally. And that's not just a poetic statement, it's a scientific fact, a consequence of stellar nucleosynthesis and stellar evolution and the cosmic cycle of matter. And maybe, just maybe, that knowledge changes how you see yourself, how you see your place in the universe. You're not separate from the cosmos, you're not an outsider looking in, you're part of it, intimately and inextricably connected to it through the atoms that make up your body, atoms with a history that stretches back billions of years to the cores of ancient stars. And those atoms will have a future too, continuing on in new forms long after you're gone, participating in the ongoing story of the universe. And that's the story of the birth and death of stars, a story of transformation and recycling, of creation and destruction, of matter and energy flowing through space and time, creating complexity and structure and beauty, and, in at least one corner of the universe that we know of, life and consciousness and the ability to look up at the stars and understand them, to tell their story, to appreciate their beauty, and to recognize our profound connection to them. It's a story that's still being written, still unfolding, and we're privileged to be part of it, to exist in this brief, bright moment when the universe is full of stars and full of wonder.